It just black screened. And
might as well since you have the Samsung watch.
yeah, it's hard to, I've got too many. There's some apps I have that you can't get through iOS that I use to control like home automation stuff that I've built. I don't want to give all that up. So, okay, y'all ready? All right. I'm guessing most likely you're going to have a quiz on Thursday. Okay, we'll have our first quiz, and it'll cover everything, or it could cover anything that we've done up to this point, including what we do today. All right? We're going to start antiderivatives today, and we'll finish this section up, and we'll probably spend the last 10-15 minutes talking about the next section, which is substitution. And once I get through substitution, we'll really probably be at a point where we're into uncharted territory for anyone who hasn't taken Cal 2 before or didn't take it in high school. Once we get past 5.5, then it's brand new. So I'm saying this because I know some of you had me for Cal 1, and we got up through 5.5. We started talking about 5.5. So Thursday, it'll start to become new stuff, all right? All right, so antiderivatives. I wanted to see, first of all, if how many of you from Cal 1 saw this formula where, like, let's say that you wanted to take the antiderivative of x squared, that you would do something like this. It would be 1/3 x cubed plus some constant. Just show of hands, how many of you saw that? Okay, so hands up people who did not see it now. You were in my class. Oh, okay, you're just playing with your... So you have not, okay. Okay, when I go through it, you know, I'm gonna go through it, I'll try and be thorough, okay? But if you have any questions, you just need to kind of like, hey, what's going on there? All right, so I will review this. I would just want to get a feel for where everyone was, all right? So first let's talk about antiderivatives. When you have a function little f, all right, we call capital F its antiderivative. So capital F is called the antiderivative of little f on some interval I, that's an I, if the derivative of this guy right here is equal to that function for every x within that interval. All right, so that's just definition. If we can find a capital F, it doesn't always have to exist, all right? But if there is a capital F that is the antiderivative of f, then capital F of x plus c is what we call the most general antiderivative of f. And c here is any constant. So we'll start with a visual example just to kind of get us thinking. Let's take a look at the function f of x equals 2x, little f. If I graph that, what is it? If I graph that, it's a line, right? That's a line. And so when I take its antiderivative, I'm trying to find a function, capital F, that when I take its derivative, I get this, right? So it's, I think, obvious to most of us that you take derivative of x squared, that gives you 2x. But if I add any constant to it, I would still get this if I took the derivative, right? Because when I take the derivative of a constant, it's always going to be 0. So what we get here is a capital F that has to be x squared, but this number c can be any number, right? Any scalar. So if we look at it visually, the red line here is 2x. That's little f. And the blue curve here is a parabola x squared, and this one in particular is x squared plus 0. That is an antiderivative, isn't it? But that's not the only one. I could also move that thing up and down, right? Adding a constant to the outside of a function like this, adding 2 just moves it up, right? So imagine all the parabolas that I could have in here, right? Moving up and down, all of them are antiderivatives of 2x. So I can show you them, and you start to get kind of what I'm calling here a family of functions. So you start with the single function, this line. The antiderivative of that is a family of functions. And they all have something in common. What they have in common is that if I go to a particular x value, and it's kind of hard to see the, okay, you see that little line, those lines moving around there? Those are tangent lines. I just had the computer draw me some tangent lines. So if you go to any x value and you go to the corresponding points on all these curves, any curve in that family, and you take the derivative, they all have the same slope, don't they? And that means that the derivative is the same for all of those functions. And the actual slope of that line is the y-coordinate of this red line. Or sorry, the slope of that line, that tangent line, is equivalent to the value of this function. So this red function would be negative over here, which corresponds to a line that's pitched downward. Okay, so that's visually what we get. The main idea is this. Someone gives you a function. The general antiderivative is a family of functions. You don't know which one it is. It's all of them, right? Okay. Another example here. This one, it might be a little more difficult to just look and see what the antiderivative of this is. All right, just looking at it and say, oh yeah, sure, the antiderivative is this. But we could verify it. Derivative of x cubed is 3x squared. Derivative of 5x squared is 10x. Derivative of 6x is 6. And the derivative of any constant is 0, right? So this matches up. This is the general antiderivative here. And again, visually, the red one is the little f. The blue one is the capital F. And if I move that, if I start adding different constants, it's going to move this blue one up and down. And all of them together would give me some family of functions, right? There they all are. They all have that same tangent line property. At any point, they all have the same slope. I can put a bunch in there, I guess. So there's your tangent line moving around there. All right, that's the visual. What we want to do is we want to make sure that we know what the antiderivatives of common functions are. Now this table's in your book, but I thought I'd go through it here and point out the most important aspects of this. The first thing here says, let's say you have a function where you have a constant, little c times the function, and you want to find its antiderivative. What does this property say from here to here? What is it saying that you can do if you take the antiderivative of this, you should get this? What is that telling you? The constants are going to come for the ride, right? So this happened when you had derivatives back in Cal 1, right? Like if I put here, here's 5 sine x, and I ask you, what's the derivative, Cal 1, you would kind of ignore the 5, right? The 5 would just come along. You would put the 5, and then you'd say times whatever derivative of that is, and you would put cosine x. All right, that's what we did in Cal 1 with derivatives. What this property is saying is that when you go backwards with antiderivatives, it's the same property. If you have a constant out there, you just need to find the antiderivative of this, which will be capital F, and the constant just comes with you. It just gets tacked onto the front with multiplication. All right? The next property says that if you have two functions that are added together, then the antiderivative will be the antiderivative of each one added together. So that's telling you can do them separately, right? And that's exactly the way it was with derivatives. If you had two functions separated by addition or subtraction, you would take the derivative of each one separately. This property is saying you can do the same thing. And it also works with subtraction. If there's a minus there, then you would subtract the two functions. So plus or minus. Okay? Now the next property right here, it's actually, this one right here. Okay? That is known as the power rule. And that's an important rule. I'm going to do a lot of examples, about 3 or 4 examples after this, where we're going to be using that rule. And all it's saying is this. If you have x to any power except -1, all right, that if you want to know what the antiderivative is, this is it. If you just like formulas, there's a formula. But I don't like to write it this way. I like to write it this way. 1 over n plus 1, x to the n plus 1, which is the same exact expression. I just took this n plus 1 on the bottom and slid it out as a fraction, 1 over n plus 1. So just let's think about why that formula works. If I asked you to take the derivative of this is x to a power, right? So what's the first thing you do when you have x to a power and you take the derivative? What do you do with that power? You bring it out front, right? So if I bring n plus 1 out front, what's going to happen when it gets here? It's going to cancel out with that n plus 1. So there's just going to be a 1 in front here. And then what's going to happen to the power? It goes down by 1, right? So you subtract 1 from this and you just get n. So when I do the derivative of this, I should just get x to the n. That's this. So if we're going backwards, right, we have to add 1 to the power, but we also have to put this out here to kind of counterbalance what's going to happen when that power comes out. Okay? Now, this rule works as long as n is not negative 1. So please notice that this right here is the same as x to the negative 1, isn't it? 1 over x is x to the negative 1. And do you see why this wouldn't work in this formula? If n is negative 1, what's going to happen in this formula? Try and put negative 1 right here. You get what? Division by 0, right? So the formula will not work. But we actually know what the antiderivative of 1 over x is because in Cal 1, hopefully you were shown that the derivative of the natural log of x is 1 over x. So we can go backwards just from our knowledge of Cal 1. Now we put the absolute value here because our natural log's domain restrictions. We don't want negative values in there, right? So make sure if you ever take the antiderivative of something like this that you throw that absolute value on there. Now I should point out that none of these have that plus c, that capital C. Notice that none of these do. And that's the book, the author just chose not to do that. But look at what they wrote up here. Particular antiderivatives. So this is really all of these is that capital C is 0. So it's just, he's just giving you an example of one of the curves. But we are going to want to put plus C on everything if we're asked for the general antiderivative. All right, let's go through the rest. These are going to go a lot faster. Antiderivative of e to the x is itself, and that's because the derivative of e to the x is itself. Antiderivative of cosine is sine because the derivative of sine is cosine. This one's a little tricky. Antiderivative of sine is negative cosine because of the negative that pops out. So we have to account for that. So just be careful on that one. And these two, those just come from, again, your knowledge of Cal 1. We should know that in Cal 1 the derivative of tangent was secant squared. So if we're ever asked to find the antiderivative of secant squared, we need to know it goes back to tangent. And then same with this one, secant x tangent x goes back to secant. We good? Okay. I'm sorry if this is a little annoying. I was watching one of the videos the other day. I was like, yeah, that ruler is kind of annoying. But hey, I can smack people if I need to. All right, so these two, this is what we covered in class, right? Beginning of this, our first day, inverse trig functions and their derivatives. So now we need to be able to go back. Now notice I'm only listing, or the author only listed 2 of them here. And that's because these are the most common ones that come up. So what we want to start thinking is whenever we see something that has a form where you have a root and you have some number here, it's going to turn out that that doesn't have to be a 1. We'll have a way of dealing with it if it's not a 1. And then you see some quantity squared here, you should in your mind start to get triggered this idea that that's probably connected to the antiderivative being arcsine. All right? Same thing here. You see 1 over 1 plus something squared like that, you should be thinking arctan. And then these two are the last 2 they have on here, and those are pretty basic. We don't do a lot of hyperbolic stuff anymore. Like we pretty much ended with that section. There will be some problems that pop up here and there, but really it's kind of behind us, all right, the hyperbolic. Any questions on the rules?
Why isn't there like any like antiderivative for like the inverted sine?
You mean, is there an antiderivative of arcsine of x?
Yeah.
Yes, there is.
Why-
That's about 3 sections away.
Okay.
Yeah, we could say what's the antiderivative of this right now. And right now, I can't show you why it is what it is, because I haven't shown you the technique that we're going to use to do it. But hey, these are all functions, right? What are their antiderivatives, right? You can say that for any function now. So, cross that bridge later? Yeah? Okay. All right. One thing no one has mentioned, what about this? I didn't see a property if you have like little f of x times little g of x. Like, is there a property for the antiderivative? I mean, if that's a plus or a minus, we're in business, right? We do each one separately. But what about if you have a product? Is this just, you know, you find the antiderivative of this one and then multiply it times the antiderivative of the little g and just, boom, you're in business, put plus c and move on to the next problem? It can't be that simple, right? I assure you, if it was this simple, Calculus 2 would not be hard, okay? Because we would be able to do all these integrals that we haven't talked about. We'd be able to do all these antiderivatives without much effort, right? And this is actually, the fact that this is not true is what makes it so hard, because we know in Cal 1, the derivative of a product was the product rule, and the derivative of a quotient was the quotient rule, and those were weird formulas, right? Well, when we try and undo something that has products in it, we have to always account for that chain rule and the product rule, and that becomes messy, real messy. So unfortunately, we can't do this. So like if I had this, to illustrate what I just said, if I had this right here, x cosine x, if I asked you to find the antiderivative of that, you could not say, okay, well the antiderivative of x by itself is 1/2 x squared, right? That's what it would be. And then you can't say times, what's the antiderivative of cosine? Sine? That's not the antiderivative. How could you prove that? Just take the derivative of this, right? And I guarantee you it's not going to be that, okay? So we'll have to be careful with that, and that problem I just did right there we can handle later also, just not yet. And it's actually the same technique that I would have used to get that Arcsin. It's called, anybody know? No? It's when we get to a section called integration by parts, that's what we'll be using for that. Okay. All right, let's do some examples. This is just going to get us comfortable with that table that I just put up there, and especially get us comfortable with that power rule. All right, we want to make sure that we can do this. You're going to be tested here on your ability to manipulate fractions. All right, there's not a big part of this problem that's actually calculus. The only part of it that's calculus is a formula, but the rest of it is just algebra. All right, so when I look at this, I'm trying to find the antiderivative of this. When I say that, I mean find the general antiderivative. So let's find the most general one. We're going to add a plus c at the end. So when I look at little f, I notice that I have 1, 2, 3 terms, right? 3 terms. And so I can do them individually. And really the only thing I have in my arsenal right now in terms of finding antiderivatives is that power rule, or it's got to be something that I recognize. So all of these, this is a power of x, right? So I should be able to use a power rule here. Is this a power of x?
Yes.
Yes, you can convert from radical notation over to that other notation. What's that other notation? Like if you have this is really x to what? The 1/2. So this is called rational exponents. This is called radicals. So we learn about this in college algebra, and the reason we learn about rational exponents is because in calculus, it's better to work with this than it is to work with this. So that's definitely a power of x. Is this a power of x?
Yes.
Yeah, see, look, right now it's 2 things multiplied. That's why I was telling you, you got to be careful. If 2 things are multiplied, you can't do them separately. But this is really just that, right? And if they have the same base and different exponents, you just add up the exponents. So this should be x to the 3/2, right? We will not say, we do not want to, I mean, it is equal to this, but we will not use this notation. Okay? We will not use mixed numbers in this class. All right? Never. So get that out of your mind. I was trying to show my college algebra class, well, I was trying to explain to them why we don't use mixed numbers here, or why we don't prefer them. It's for this sort of thing. We want to work with the, what is this? This is called a mixed number. What's that called? Anyone know? Improper fractions. So we want to work with improper fractions anytime we're trying to represent something in its rational exponents. All right, so I have an idea of what all those are going to turn into. Let me go ahead and just rewrite the problem. I'm going to rewrite little f. It's going to be 2/3 x to the third, nothing to really redo there, plus 4x to the 1/2, and then minus x to the, what did you say, 3/2, right? Okay, now, working on these one at a time. I'm going to try and get capital F now. I have multiplication here. This is a constant in front of a function. That means that the constant's going to just come along for the ride. That was that c in front, okay? So I'm just going to write down 2/3. Then I'm going to put times. Now I'm focusing all my attention on this. That's x